Welcome to the 17th lecture for Physics 4B. We wrap up our coverage of DC circuit analysis with this lecture. Next time we return to circuits, we will be handling time-dependent and AC circuits. Here, we continue with our applications of Kirchhoff's rules. For the first example, we actually don't need Kirchhoff's rules, and that is the point of the example. As you become familiar with the circuit's problem solving, I encourage you to develop your intuition and judgment so that you use the right tool for the right job. For easier questions that can be answered by simply combining resistors, they should be answered that way, without using the heavier machinery of Kirchhoff's rules. And we have a couple more examples of simplifying a resistor network and a short discussion on handling capacitors at this stage. And we introduce a calculational tool that I hope you will find useful, a computer algebra system. I do have a longer demo of Wolfram language based on Mathematica, but as you will see me using SageMath for most of homework help videos in this class, that's the demonstration example you will see in this lecture set. And in the last couple homework problem-solving examples, you will see me using SageMath. For the first of the two, I don't need the CAS so much. I picked this problem to illustrate the arrangement commonly known as voltage divider, which is a very useful module in a lot of different circuit and filter designs. The second problem is the kind of example where the problem solving becomes greatly simplified through the effective use of a computer algebra system, as you will see. Again, this is it for our coverage of DC circuit analysis. Depending on the approach you have taken, either you have the magnetism lectures or the time-dependent circuit lectures next. I will see you in those lectures.
Welcome back. Let me actually go over problem 3 before I ask for your request so that I can illustrate something about power. We won't go through it in detail, but let me just do that. By the way, so when you're solving circuits, I want you to start using your judgment. In the sense, the method starting from Kirchhoff's rules, these are like a standard strategy, as in any problem can be solved using this. But that doesn't mean I think you should actually use this for every problem. When you look at a problem, look at it for the first time, I want you to first try to see, can I answer this more simply? Because, Kirchhoff's rules, when you're using it, it's a whole process that takes a long time. You have to define the junctions you are going to use, you have to define the loops, you have to write down equations, you have to go through the algebra. It's a multi-step process. It's like, the kind of thing you would do if you are sitting down for fancy dinner. You don't do that every single time you are eating a cup of noodles. So you have to use your judgment whether a problem like this is complicated enough that you have to use your full-featured problem-solving tool set, or if you can use some shortcuts to answer it quickly. Here I say use the shortcuts. So we derived these formulas in class a while ago, I think Monday last week. Hopefully. So maybe Wednesday. You first ask yourself this question. Can I answer this question using only these simpler high school physics tools? And the answer is yes. These two resistors are in parallel, so I can add them in parallel. Once I do that, then this and the other resistors now in series, so I can add them in series. So what I would be saying here is, all right, these two resistors, I can add them this way. So when I consider these two, it says though, imagine erasing these two. I'm not actually going to do it there because I have some other purpose for that. Imagine replacing this with a single resistor. And that's what those formulas mean, that if I replace both of these two, both of these with a single resistor of equivalent resistance, then that's the formula. Then that's the formula that tells you what that equivalent resistance would be. So here, so 1 over R equivalent is equal to 1 over R1 or 2R plus 1 over R2, or in this case 3R. So you solve this for this, that's your answer. And I've already done it, so let me just write it down. The answer should be 6 over 5R. That's the equivalent resistance of a single resistor that does the job of both of these. Good? Once you have the circuit, now this resistor is in series with this. So you can add these two. Let me do that in different color. Now you can add these two, add the two resistors in series. Once again, I'm not saying, so that's what I mean, you have to use your judgment. So although every problem can be solved using Kirchhoff's rules, I'm telling you that shouldn't be your first approach for every single problem, because that will take too much time. Although there are questions that can be answered more simply using these formulas, there are definitely problems where you cannot solve them using this. So these are shortcuts. When you can use them, use it. That's where you need a judgment. You need to think it through, see which is the best approach. So here, the best approach is this, add these two in series, and the equivalent resistor, that's where you imagine, getting rid of both of these resistors, and imagine that you replace this circuit with a single, this simplest possible circuit of a battery, attach it to a single resistor. And this equivalent circuit that you are talking about is the one you would get by adding these two resistors in series. So 1R plus 6 over 5R. So this equivalent resistance should be 11 over 5R. Good? Yeah, so it took me longer because I was talking, but you could have done this in 1 minute. Whereas if you're setting a Kirchhoff's rules, you are not going to be able to do it in any faster than 5 minutes. So you have this circuit, and the thing I wanted to spend more time on was part B, where it asks, what is the power output of the battery? Good? So having answered oh wait, I see, it's asking the voltage change across the resistor R. Sorry, I thought it asked for a different question. But you would still go through these steps. Because to know the voltage change across the resistor R, what you have to know is the current through this circuit. Right? So this coming back to solve a circuit means to know all the current. Because any other question I might ask, you can answer it simply if you know the current. So I would still go through these exact same steps. Now, from here, to find the current is a single step process. To find the current here, it's a single step where you use Ohm's law. Here's the voltage, here's the resistance. The current is the voltage divided by the resistance, 11 over 5R. That's it.
When it says just R, does it just mean the one?
Yeah, so when it means R, so the question is asking for the voltage drop here. So that's the part where, okay, it's a little bit more complicated than I thought. You have to think it through. So once you know the current through this branch of the circuit, then now what you can say is that this voltage drop difference is going to be the current that you find times the resistance R. Yep. Okay, so to actually answer the question that they're asking, so part A asked for this voltage difference here. What is the voltage difference? Well, I found the current, multiplied by R, that's going to be my voltage difference. So my voltage difference will be the current. Let me write it down this way, V0 over 11R times 5 multiplied by R. So the resistances are cancel out. and you end up with 5/11 of V naught. Okay. So, if this is the first time you are working on circuit question, it might take you a while. So if this is first time because you haven't been working on homework and you are forgetting what we covered in lecture last week, then this could take a while. But once you are used to circuits, this is actually the simplest, non-trivial question I can ask. As in the question like these are trivial questions. Anybody should be able to answer this quickly. Like I wouldn't bother asking this on an exam. These are the kind of questions. Let me put it this way. These are easiest question that I could put on the exam because these are no longer trivially easy. They do require some thinking. But as you can see from the fact that I didn't even touch Kirchhoff's rules, it's not that complicated. Yeah. So that's the voltage. And the reason I want you to go over this question in more detail is to talk about power. So we went over the formula that power is given by this formula. So the power output of the battery, if you say that power output is the current times the voltage of the battery, well, that would be correct. As in so we can calculate this power output here. So in part B, it would be power output of the battery will be this current that we found. This current that we found, is that the same current through the battery? Yes? So it will be that current times this voltage. So you might say this power output of the battery is V naught over 11 over 5 R times the voltage of the battery. Let me simplify it. 5/11 V naught squared over R. If that's the answer you get, that's the correct answer. Once again, nothing complicated here. But the part I want you to touch on is the part that the question doesn't actually ask. I probably should ask. If this is the power output of the battery, where does that energy go? Energy that's coming out of the battery, where is that going? Yeah, it's somehow, we want to say that energy is not disappearing. It's going somewhere. It's going somewhere through these resistors. These resistors are going to heat up. And that's what we call the heating up of these resistors. That's what we refer to as, you also see this phrase in homework, that's what we call Joule heating. It's the phrase that we refer to, well, whenever you have current flowing through resistors, it's going to dissipate the energy that's associated with the current flowing as heat, because it's not being stored anywhere. Right? So the formula for Joule heating, if you look at the handout, you would see this. The Joule heating of resistor, it's given by current squared times the resistance. And you can actually make sense of this formula through the expression for power. So if you look at this simple circuit, as in single battery connected to a single resistor, yes, we're looking at this simple circuit, then what we can say is, all right, the power output of this battery would be current times the voltage. Well, for this very simple circuit, whatever power output of the battery is, that should be the power dissipated by this single resistor, right? So you would say, all right, so this should be the same thing as this. Power dissipation by resistor will be equal to current times voltage. But the thing that makes me a little bit uncomfortable here is the voltage. So here by V, I mean voltage change across this single resistor. But I want to have some expression that's more universally applicable. And although this is true, what's meant by this V is going to be sometimes a little bit confusing. So I want to rewrite this in a way that I will be guaranteed not to be confused. So what I'm going to do is I'm going to re-express this in terms of the resistance and the current, because I still have to talk about current that's flowing through it. So I rewrite V in terms of resistance and current using Ohm's law. Then V is equal to IR So with that, this becomes I squared R. So that's where this formula for Joule heating comes from. And what I want to just quickly show is that in this simple, but not too simple of a circuit, that the power output of the battery is in fact equal to the power dissipated by these three resistors. So let me just do that calculation quickly so that you see at least one illustration, and the rest of the practice you're gonna get it through homework. So here, I would calculate I squared R for this battery. So I'm sorry, this resistor. So it'll be the same current that we calculated before, times, so that squared times the resistance. So it'll be V naught over, or 5 V naught over 11R squared times R. This is going to be the power output of the first resistor. That'll be 25 over 121 V naught squared over R. Good? This is a number somewhat smaller than this, so I need to add power dissipated by these two. Okay? That requires a little bit more work, so let me once again go through it quickly. So the current through here and here, when you figure it out, what it's going to be is the voltage difference here is 6 over 11 V naught. Let me write it down and you can figure that out on your own later. The voltage difference from one end to the other end here, it's going to be 6 over 11 V naught. Figure that out on your own. When you find that, then I can now use this with this to find the current here. The current here will be 3 over 11 V naught over R. The current here will be 2 over 11 V naught over R. A little bit of a consistency check. These two currents added together is the same current. It's the same current we found before. Good. Then the power that's dissipated through the resistor 2R, that should be once again the current squared. So 3 V naught over 11R squared times 2R. So that would be 9 over 121 V naught squared over R squared times 2R. So it'll be 18 over all of this, and R cancels one of this. Okay. Let me do it for the third one, and we'll add it up and see that they agree with each other. So this third resistor, the power that's dissipated there would be the current squared, 2 V naught over 11R squared times the resistance, 3R. So that'll be 4 over 121 times 3, so 12 over 121 V naught squared over R. So, if the question had asked how much power is dissipated in each of these resistors, this is how you would calculate it. And what I'm claiming now, which hopefully intuitively makes sense, is that when you add up these three numbers, that should equal this number here without actually doing calculation. Do people agree without actually doing the calculation? Yeah. That would come from energy conservation. Whatever energy comes out over here comes out through the resistors here. So let's add them up and see. So we are calculating the total power, P1 plus P2 plus P3. We are saying 25 plus 18 plus 12. 25 plus 18 plus 12 divided by 121 V naught squared over R. Add this together, 30, 25, so 55. So this is 55 over 121 V naught squared over R. This is 5 times 11. This is 11 times 11. So it is 5 over 11. 5 over 11 V naught squared over R. So I think this is the last thing I'm going to talk about power. That the basic relationship for power is this, current times voltage. And so this particular expression is useful to keep in mind, because if you try to use this formula for the resistors, you may make mistakes on what voltage to use. People usually don't make a mistake about the current, but people can often be made to make a mistake about the voltage. That's why I give you this to you as a separate formula that you should be using with the resistors. All right, so I have something like 15 minutes. I think that's enough to probably go over some of the things and leave a little bit of time for capacitors at the end. How do people feel about question 5, this resistor network? Do people feel okay about question 5, the resistor network? What is the equivalent resistance between points A, B, and AC? People able to work that out? Yes? Okay, let me just redraw the circuit. So I won't go through the detailed calculation, but so this is a way to see how a circuit can be simplified without doing a bunch of math. So this is how I draw equivalent circuits. Essentially, the idea is that with the circuits, the only thing that matters are the connections. As long as you keep the connections the same, you can change everything else around. So let's say, let me just do it for A and B. So let's say we are interested in what is the resistance between A and B. Then, all right, let me draw a representation of point A, draw a representation of point B. And what I'm going to do is I'm going to redraw this circuit, being very sure that all the connections are done correctly. So looking at this diagram here, I see that there's a resistor that's connecting A and B. So all right, let me draw that. So A and B, one path between them is one that involves one resistor. Now that's not the only path between A and B, right? So I just drew this path. There's also this path here, right? So I'm going to draw the second path also. The second path has some junction there, but I guess let me draw it this way. So one resistor here, another resistor here. So this is a path that involves two resistors. All right. I may be running to, well, let's see. There's at least one more path. There's the path that goes through point C, right? So, all right, I have another path that has, well, another two resistors. So, and I could label this point C. All right, and so I've been labeling the path that I have accounted for as I copy them over here. There's one that that's not reflected here, right? This resistor here. Where would I draw it on this circuit diagram? To here, right? So this is where you would add this resistor. And if you're just looking at this circuit as it is, it's understandable if you're thinking, oh, I don't know how to simplify this. Because this resistor actually ruins everything that you have set up so far. If you didn't have this resistor, do people know how to simplify this? Right? They are series and then parallel, right? It's this resistor that's ruining things. And this is where I'm familiar with one, symmetry, and two, how to simplify a circuit by looking at current matters. So let me give you this rule. If any part of your circuit has no current flowing through it, then you can actually get rid of that part of the circuit. Once you can figure out there's no current flowing through there, then you might as well just open up the connection because, well, either way, there's no current flowing through it. So this is the situation that I want you to imagine. Let's say we apply some voltage difference here. Between A and B, we apply some voltage difference here. And I want to come up with an argument that says that the current flowing through here must be 0. What kind of argument can I make to say, you know what, there's not going to be any current flowing there? So I don't want to apply Kirchhoff's rules in full, because if I do, if I do that, I'm essentially going to be solving problem 6, part B. That's going to take 30 minutes. I don't have time for that. But I'll tell you that this problem is one that can be done in about less than 5 minutes from now if we know the exact correct thing to do. Let me, to help you think through this, let me ask you this question. Imagine you have 0 current flowing through this resistor. What else must also be true? Not voltage is 0, but you do want to think about voltage. The change in voltage is the 0, meaning whatever voltage is here, VC, that's going to be the same voltage here. All right, is this a statement that you can prove? How do you know that voltage here is the same voltage here? Okay, can you explain the symmetry? Yeah, like these two branches. If we swap them around, nothing would have changed. So these 2 points are the same points for all intents and purposes. You can swap them and nothing changes. So these 2 voltages are the same. Once you realize that, then you can say, oh, based on the symmetry, this is true. Current here is 0. And once you get that far, then the thing that you can do with the circuit simplification is you can say, oh, this resistor might as well not be there. And once you don't have that resistor, then you can do the rest of the question. Add in series, add the whole thing in parallel. Good. So this idea of simplifying circuit, this will be important in, so these are useful in doing simple questions. Where's my eraser? These are important in doing simple questions, and those simple questions are, question 5, once you realize the arguments that you can make, then question 5 becomes simple, and it's the exact same argument you would actually make with the question 6, part A, that you use the same symmetry here. Now, part B, where you ruin the symmetry, is where it'll take a long time, so we won't actually do that. I don't have 30 minutes to do it. So I was hoping to have some time for question 7, but it's similar enough to the other question that we did the other day, so we'll skip question 7, unless someone, well, I guess if you really need to know the answers are posted, so you can look at the answer. We'll skip question 8. You can read the answer, but I'm never really going to test you on the idea of Thevenin equivalent voltage. I mean, it's a good concept to know, but I'm not going to test you on that, so let's skip question 8. Everyone good? Okay, so once we have done that, then we have time for question 10, which is actually what I want to have a little bit of time to go over. So this is something that we haven't so far talked about in class, and dealing with this circuit, so far, you have dealt with only really 2 circuit elements, batteries and resistors. And hopefully you are feeling a little bit familiar with both of them, how batteries behave and how resistors behave. But one more circuit element that you can handle in part is capacitor. So I want you to have some sense of intuition for dealing with the capacitor in a simple sense, not in the full detailed sense, in the simple sense of, enough to answer part A here. So let me remind you of how we deal with the capacitors. So with the capacitors, this is the one relationship to remember. I called it definition of capacitance. Definition of capacitance. Capacitance C, it was defined as amount of charge Q that you store per some voltage V that you apply. Does this look familiar? Yes? Yeah. And what I'll tell you is that when you are dealing with the capacitors, this is as important as Ohm's law was when you are dealing with the resistors. This is really the thing that tells you how capacitors behave in circuit. So let's look at this circuit. It says, I want to save time involved in drawing circuits. So let me draw it this way. So I want you guys to just visualize this circuit. Imagine you have a circuit built with, so I guess the easier way to visualize it might be, first imagine a circuit made up with the batteries and two resistors. Are they in series or parallel? Imagine the switch is closed. Are they series resistors in series or resistors in parallel? Resistors in series, right? So this is if you didn't have, if you didn't have the capacitor, then it's a circuit that you know how to deal with. So the question I want you to be able to answer is, all right, now let's imagine that we are adding this capacitor. How should we handle this capacitor? And here's one complication that this will introduce. This capacitor will make the circuit time dependent. So the effect that this capacitor has on the rest of the circuit will be a function of time. And that's something that I don't expect you to deal with on exam 2. But what I think we have enough time to get at in the 3 minutes or so that we have is to look at how the time dependence of capacitor works out, so that you can look at it, you can answer this really for two very specific times. One is, one that I want you to be able to answer is, how does the circuit look at time equals 0? As in, the moment you close the switch, how does the circuit look? Right? And I want you to be able to, what do you think the other moment in time is? Well, not when, so let's say we close the switch at time equals 0, and we're just going to leave it there. So I say, okay, I'm interested in how the circuit looks the moment you close it. And there's one other moment in time that I think you have enough to reason through. Yeah, infinity, after a very long time. So in other words, so the other picture that I think you can work out is a circuit that, well, as time goes to infinity. The opposite of 0 is infinity. So I think we have 2 minutes or so, and I think that's actually enough to work this out. So since the capacitor is time dependent, we have to specify some initial conditions, how it actually looks like at time equals 0. And this won't be arbitrary. This will be based on your physical intuition. As this is a capacitor. You've seen the capacitor, right? The moment, so this is connected to this circuit, and initially the switch was open, and at time, imagine the capacitor just before we close the circuit. How much charge do you think is on the capacitor? 0, right? If it had any charge on it, yeah. So the natural state that you can imagine the capacitor to be at is, so before closing circuit, before closing, the charge on the capacitor was 0. That's a very natural assumption to make. And sometimes problem will tell you that directly. So this is what I want you to reason through. Let's say at time equals 0, I closed my circuit. How much charge do you think should be on this capacitor now? The fraction of a second after I close the switch. Still 0, yeah. Because whatever amount of charge on it, it can change at some rate. And the rate of change of the charge will be the current. So this is where you can actually write this down. If you have if you are given some amount of current flowing through the capacitor, you can definitively say that is equal to the rate of change of the charge accumulating on the capacitor. Now, in most circumstances, this current is going to be, it's not going to be infinity. It's going to be some finite number, which means for some finite amount of time, or if this dt is equal to 0, then your dq will be 0. So that's where I'm trying to explain the intuition that Kevin was saying, that the moment you after close the switch, the moment after closing at t, or moment after closing, you would say that amount of charge at t equals 0 is still 0. That in the infinitesimal time before closing not closing the switch and closing it, this one changes suddenly. Good? So let me ask you this question. What do you think is the voltage difference between one end of this resistor and the other end? So this is how I want you to think through this circuit. So I want to figure out the voltage difference from this point in the circuit to this point in the circuit. What else is directly related to this voltage difference? I don't want to quite, because I really have no way of finding this directly. I want to get to something else that I can actually find out in a single step. So there's something else that's equal to the voltage difference from one end of resistor to the other end. Some other voltage in this circuit that's equal to that.
The voltage after the first resistor?
Yeah. So once again, that's what I'm trying to get at. I want you to.
Is the voltage different to the battery?
No, the voltage here is not going to be the same as battery because there's this resistor here. If there's current flowing, the voltage will change. Yeah, voltage of the capacitor. That's the thing that's connected in parallel to the resistor. Remember, definition of a parallel means that they have the same voltages as they do here. So voltage difference across the capacitor, what is it? No. We just talked about it. Well, okay, we didn't just talk about it. So if we want to know the voltage of the capacitor, the very first thing you go through is the definition of capacitance. That's why I'm telling you now that this is as important in dealing with the capacitor as Ohm's law is in dealing with the resistor. So whenever you want voltage difference across a resistor and you have the current, you would go through Ohm's law. So here, we know something about the charge on the capacitor. So now when I'm asking the voltage change across capacitor, I go to the definition of capacitance. So we know Q is equal to 0. What does that tell us about V? Also 0, yeah. So this gives you a direct relationship between amount of charge and the voltage difference across it. All right, I guess I underestimated how much time this would take. Well, I'll just give you one more statement so that I can at least wrap up what we started without having really time to give you intuitive feel for it. So the circuit at time equals 0, let me just wrap this up. We said circuit at time equals 0, this Q at time equals 0 being 0, this means that voltage difference across the capacitor is equal to 0. Yeah? And for the circuit at some infinite time, so this I'll just have to tell you what it is without really explaining why. At this point, what we can say about is the current through the capacitor, this should be equal to 0. And that really follows from this relationship here. Because at some infinite time, we are assuming that the charge probably won't be changing anymore. So at the moment, well, current will be 0 because charge is not changing anymore. And you can simplify circuit with the help of these two rules. With the help of these two rules, you can simplify circuits dealing with the capacitor either by replacing capacitor with a piece of wire, meaning 0 voltage change, or by replacing the capacitor with an open circuit, meaning 0 current flowing. And which one you use depending on the circumstance. There are some homework questions where you would practice it. But so your homework, it's not homework. Your exam does include the capacitor. As in, we did talk about definition of capacitance 2 weeks ago. And dealing with the circuits that have capacitor on it, if it comes up, it'll be a small portion of your exam. But it's something that you are expected to be able to handle because all this is application of something that you already know. It's not something new that I'm springing on you 2 days before the exam.
So that's one way to get it. Now, this is great for small and simple system of equations like this. The challenge you will run into is that, especially in a real world type application, where you might have a system of 500 equations. Then, 500 would be small system of equations if you're doing anything like finite element analysis. So you might have a system of 10,000 equations, and it'll be generated in an algorithmic sense. So you wouldn't be writing it down one by one. When you're doing that, this simply will at some point stop working, or you will need a better way, or you will need to get need to be able to get access to lower level of representation so that you can use more specialized optimization functions or whatever. So this is something you might have seen in your college algebra class, which is this. When you have a linear system of equations, you can actually turn that into, you can represent it as a matrix multiplication. So I can rewrite this into a standard form so that I can represent it as a matrix multiplication. Once I've done that, I can redo this exact same calculation, except as matrix multiplication. So let me do that here. I need to do a little bit of by hand algebra. So let me do that over here using my Zoom annotations. This is probably visible. Okay, so I'm gonna rewrite equations 1, 2, and 3 into the what could be called the standard form, which is I'm going to treat the currents as each individual terms, put all the terms linear to it on the left-hand side, and put any other terms, the what is it called, the inhomogeneous terms, on the right-hand side. By the way, I could be using that term wrong. It's been a while. I know what things are and I know how to use them. I don't necessarily know what they are called. So I'm rewriting the first equation so that it's I1 minus I2 minus I3 is equal to 0. I'm rewriting the second equation. So the second equation doesn't have any I1 in it, so it's a 0. And I see that plus I need to do this in correct orders for the next step. I'm going to write down the coefficients first. So it's going to be R2 times I2, and then minus R3 times I3. And I need to move all the other constant terms over to the other, or the terms that don't multiply to any of the current terms. So that's going to be V2 minus V1. Just to making sure that's the exact same sense in which I use them here. Yeah. So, okay. The last equation is gonna be, oh, I need to decide, well, either, it's gonna have a lot of minuses. Let me imagine multiplying through by -1 first, then it's gonna be R1 times I1 plus R2 times I2 plus 0 for the third term is equal to, and imagine having moved over V2 and then multiply through by -1, so it's going to be V2 here. So this is the equation in standard form. Having written it this way makes it easy to kind of visualize the coefficient matrix, which you might remember from your, again, college algebra, or I think it might be our Math 1 class if you took it. So these are the coefficients: 1, -1, -1, 0, R2, minus R3, R1, R2, 0. And this is what I mean by coefficient matrix. Let me write it down, then I think you can see it more easily rather than me trying to say out loud what it's going to be. So I'm going to rewrite this system of equations as a square matrix multiplying to column vectors. So I have the first 3 by 3 square matrix, 1, -1, -1, 0, R2, minus R3, R1, R2, 0. And let me set this up with the column vector, I1, I2, I3. And you can see, check for yourself later, maybe, that when you do this matrix multiplication, so you are going to get 3 by 1, it's row first and then column, right? 3 by 1 column vector, and the first element of the column vector will be 1 times I1 minus 1 times I2 minus 1 times I3. So it's going to be this expression here. And the same thing for the second row and the third row. So you can represent the above system of equations this way by having the left-hand side of column vector equal to this right-hand side. Oh, wait, I need more space here. So let me leave a little bit of space. Equal to 0, V2 minus V1, V2. So, I mean, so far, this is just a interesting way to rewrite a system of 3 equations into one equation involving matrices. Now, what's more than simply interesting is if you represent this as a square matrix, a linear operator that I might call A, and if you can somehow find the inverse of this square matrix, A minus 1, then you can do this. You can take this entire expression, multiply by A minus 1, A inverse on the left. Then, and with the matrix multiplications, you have to be careful about the left and right order because they don't commute. Then on the left hand side, A inverse times A will cancel out. You'll get 1. So you get I1, I2, I3 equal to the A inverse times the, I don't know what this is called, this column vector. I don't know what it's called. The constant vector? Anyways, so if you have access to a system that can take inverses of matrices for you, then solving this system of equations can be done in this very automatic, programmatic way. And the system that can take inverses of matrices for you is computer algebra system. That's kind of the key feature of a computer algebra system. If it's a symbolic computer algebra system, which I think they are almost by definition like Mathematica, then they can do this symbolically. And even the programming languages that can't do symbolic operation, like MATLAB, without the symbolics package, or Octave, if we are using MATLAB, free MATLAB clones, they can take inverses numerically. There are algorithms there for that. And so if somehow all these parameters values were known numerically, then you can do this numerically. So let me do this exact same calculation here using Mathematica. And we'll just verify that the result we get matches the result we got using the built-in functions here. So let me set that up. I need to define the matrices. Let's see, A is equal to, and I hope I remember my matrix notation right. This is the first row, and then the second row, and then the third row. Okay, so that's going to be matrix. I'm pressing just to enter because I need to define additional variables. I'm going to build a vector. Let me call that V. So I press the escape, typed in V, and I'm pressing escape again so that I have access to the correct symbol. So that's going to be a column vector, 0, V2 minus V1, V2. Okay, so those two are the variables that I need access to. And what I'm going to do is, One thing I'm not sure is if I do A times phi, what does it do? So, once you have matrices, you have to start worrying about, are you talking about multiplication as a matrix multiplication or element by element multiplication? Like there are so many kinds of multiplications. I want to make sure whatever operation I do is the matrix multiplication, not element by element. Okay, yeah, this is giving me something that's weird. So I'm pretty sure this is an element by element multiplication. Let me try this. I think that's going to be the matrix multiplication. Yeah, okay. So I need to use the period. That's one. Matrix multiplication is in Mathematica. So I'm going to take inverse of A. The thing will do that for me, times matrix multiplication, the column vector, that's the thing on the right-hand side. Then the resulting column vector, the first element should be I1, second I2, third I3. So it's hard to compare this with that. They look different. Let me run it through a simplification just to be sure. Postpend with simplify. And they look the same, I think. Yeah, so this is how you make use of computer algebra system. And this operation, this kind of set of steps is basically the exact same step you can use on any computer algebra system, being mindful of their own syntax, programming syntax. So it's this procedure that I want you to demonstrate, because whenever you are dealing with a complex physical system, it's probably going to involve solving a system of equations. And the more complex a particular model or simulation is, the more number of system of equations you have. And at some point, you just have to do it with a program. You cannot expect it to solve a system of even 10 equations by hand. It gets too time consuming and unwieldy. And so yeah, Mathematica is one of the well-known industry, standard computer algebra system, but which costs money. You can access a version of it for free at wolframcloud.com. Now, I want to show you one that won't be limited the way the Wolfram Cloud is, because they give you access to a basic version so that you will have incentive to upgrade, which means they needed to limit you in some way. So what I want to show you is the other system that's completely free. And the first time I saw it, like about 10, 12 years ago, it was pretty much unusable. But when I looked at it a couple of years ago, when our mathematical license was running out, it was actually much more usable now. So I think, I do need to put in this disclaimer that I'm not as familiar with it. I'm not as like Mathematica syntax. This is what I've been breathing for however many years I was in graduate school. So all of this, I just know it by, except for the weird multiplication thing. I know most of this by memory. This SageMath, I will often have to look up the syntax. So with the disclaimer, it's still what I would recommend, really for two reasons. One is price. It's free, and it's free in the sense, not just in terms of price, also in the sense of license. So it is free price-wise because it is a free and open license attached to it. People can try to sell you that. Like sometimes people have a value-added version of it that you might buy, but the underlying software packages are free. So somebody will always make a free version available on the internet. So it's free. That's the number one reason. And second, it's the syntax for this is based on syntax for Python, which is one of the most popular languages. I mean, it has its limitations, but a lot of work in computer science these days are done using Python. So it's a good language to learn. And since this system uses the Python syntax, it'll help you become familiar. So
I'm going to show this to you in two different ways. One is there's an online version of it. If you go to sagecell.sagemath.org, that'll give you this, take you this place where you can actually run code on this system without installing anything on your computer. So let's say I want you to integrate, but I don't know their syntax for integrating. So you say help integrate. Then when you click evaluate, it brings up the help function. This is how the documentation on Python system looks like. So this is their documentation. One of the example is, oh, I can do this. Integral sine of x with respect to x, and integral sine of x with respect to x, and get that. Oh, let me try sine squared x squared. Yeah, it's giving me that special function-based representation of that, which is, yeah, anyways. Oh, I wonder if I can do integral of that from, oh, I don't know the syntax for it. So help, integral. How to specify the lower and upper limits. There it is. That's the lower and upper limit. Okay, so lower limit, let's say 0, upper limit 1. Then I think this will it do numerical integral? No, it's doing interesting. It's doing the symbolic thing, which I'm fine with. Is it an integral? I don't know. Let me just do this one last thing. Is there a numerical version somewhere? Oh, a numerical approximation. Let's see. There it is. So it's having me do this. I think I can actually do it this way. So that'll give me a result. And I think n is a function of like a function itself. So let me try that. No, it's not. Never mind. So I need to put the result into a function and then f dot n. It's a bound method or something like that. So, why doesn't it? Oh, because yeah, that's not. Oh, then let me just go back and retry this. I don't know. I'm just playing. Again, I'm not super familiar with the syntax for SageMath. Yeah, there it is. That's the same result that we were getting earlier on Mathematica. So yeah, you can just run code here. And I wonder if for the purpose of what I'm demonstrating here, if it's just easier to do this. Let me do that first, and then I'll do it one more time using a version that you can install on your computer. Because this does kind of, it's limiting. It's limiting in the way, so there is a reason Python is popular. The reason Python is popular is it's not a compiled language, meaning, so program languages like C and C++, they are compiled, which means, well, they're compiled. And what that means is it precludes the possibility of an interactive session. Python is an example of what's called a scripting language, or I think that's the correct term, which means you can have an interactive session. So within the interactive session, you can basically do what you saw me do here, like do line by line. Here's an input 13, here's output 13, input 14, output 14. And this kind of helps you learn the language as you go. And on this thing, it's kind of hard to do that because you have one window where you type in code and you click evaluate once, and it gets limiting at some point. And it might be useful to have it installed on your computer to do it properly. But let me just reproduce what I did with the Mathematica here, just using the online version. So I don't want to get rid of those, but let me get rid of that. I don't think I need them anymore because I basically have a version of that equation in the form of this coefficient matrix. So I already have it. As long as I don't get rid of this window, I'll be fine. So, I can actually do exactly this here as well. SageMath has its own solve function, and there it is. And you can use that exact syntax here as well. Now, one difficulty you will run into is, let me just try copying and pasting this line to see if SageMath handles that. My suspicion is it doesn't. Yeah, it complains about this. This is why when I had the help documentation for solve, it had this weird line that declares what the variables are. So, all right, I'm gonna need to declare my variables. I don't quite know why I have to. I just know that I have to. So I1, I2, I3, R1, R2, R3, V1, V2. Those are going to be my variables. And apparently this is the syntax. Let me copy and paste. This is the syntax in which they are declared for some unknown reason. Okay, and I can put in basically a version of this for solve using the syntax that I see here, which is the system of equations enclosed in square brackets, and declare the variables I want to solve for one by one. So system of equations, that I1 equal to I2 plus I3, and V1 minus, and this is where I have to be careful. SageMath doesn't have implied multiplication. So I have to do I3 times R3 plus I2 times R2 minus V2 is equal to 0. And the last equation, V2 minus I2 times R2 minus I1 times R1 is equal to 0. That's the last one. And my variables are I1, I2, and I3. And I can run that and get the result. And if you kind of stare at this, just this portion, and compare that to this, and you should see that they are the same. And hopefully then, well, once you expand out this parenthesis stuff, then they're the same. Then it's all right. I'm not going to check the remainder, but they are probably the same. So yeah, that's one way in which you can use this to solve this system of equations. And it's the same deal as the same applications as Mathematica, in that you might have a situation where you have a system of 50 equations, and this could be very limiting. It's not very amenable to programmatically building up your system. So at some point, you'll want to go to this model where you build up the coefficient matrix and you take an inverse of it and then multiply it. So let me do that on here. So I need to, well, I'm still going to need to declare my variable. So let me leave that alone. And my coefficient matrix will be, I think it, let me look up matrix syntax. SageMath matrix. Oh, well, let me just pretend I didn't search before. Okay, there it is. So this is how you can look up helpful documentation. I think 9.1 is the latest edition version, and this is kind of showing you with examples how you'd be using it. And actually, it has one very useful thing, which is that it tells you that this asterisk symbol represents matrix multiplication. That's kind of different from what the syntax was for this. So different languages, you have to be aware of their own syntaxes. I would say, this is actually more common. The whole element by element multiplication, that's like mathematicians would just recoil at that. It's such a ugly operation in terms of more abstract math. So I fully understand this. This is more natural. So anyways, that's the syntax I have to use. I have to use matrix function and build it that way. I hope that capitalization is okay. I'll just follow it. If that's supposed to be lowercase, the system will complain. So matrix. So I'm just going to copy over the matrix. 1 minus 1 minus 1. Oh, wait. Yeah, I need more square brackets. So that's the first row. And then the second row, 0, R2, minus R3, R1, R2, 0. Okay. So that's matrix A. And phi is going to be vector. I hope this means it'll create it as a column vector. I hope. 0, V2 minus V1, V2. Okay. And let me just do a test run, 8 times phi. This should give me an output of a vector with the 3 elements. It doesn't actually solve anything. It just gives me an output. That takes super long for some reason. It's possible there's a typo. I think. Yeah, I'm pretty sure there's a typo. Someone probably should tell them to fix that typo. I don't know what the system does with the half-run code. I hope I'm not doing anything terrible to the server. Yeah, so it gives me the result. It's a result with 3 vectors. This is the first element, or not 3 vectors, a vector of 3 elements. Second element, third element. Okay. Now to actually solve it, you need to be able to invert the matrix. So I think I have an idea what it's called. Help inverse. It's not defined. Oh, I know. There's actually a bound method that's called inverse. Let's see, invert. What? SageMath invert matrix. Computing inverses. There it is. Yeah, okay. There's supposed to be a bound method. That's just a Python term. So let me write down that thing. Okay, I pasted in what I copied out. So if A is already a matrix object, so if I do A, this dot, it doesn't represent the multiplication. It's an object-oriented programming thing. I'm accessing the functions that are bound to this object A. And one of the functions is called inverse, which takes this data that's stored in the object and does its algorithm thing to compute the inverse of that thing. Okay, so that's the inverse matrix. Multiply that to phi. That should get me the inverted matrix. So that should get me the solution, I1, I2, I3. And now when I do that, so you get the solution, but you get the solution in a form where it's very hard to see if this is the same result as what you see over there. And so this is where I think I want to finish up the remainder of this in interactive environment. So you can download and install SageMath yourself. I think if you follow this link here, it'll show you one of the places where you can download it for any operating system you might be using. I just downloaded and installed it on this computer just before this class session. Here it is. That's my SageMath. I'm running it. It has other features like a SageMath notebook, using something that I didn't want to bother with. So I'm just using this almost like I would use a Python, interactive shell, which is its own thing. And I don't know. These are just warnings, so I'm just going to ignore them. Hopefully, future update will fix that or something. So what I'm going to do is I'm going to basically run when this finishes initializing. Takes super long. I don't know why. It's annoying. When it finishes initializing, I'm just going to run this code one by one. And that's really the biggest benefit of having an interactive environment, because you don't have to do this constant thing of modifying the code a little and then re-evaluating. You can just do it line by line. That's much better. So Control C to copy, and then does it do Control V? It doesn't. So right click and then paste, Shift in. All right. So this initializes my variables. Let me copy and paste this to define my matrix A. Oh, okay, Shift, Insert. Where's my insert? Okay. Okay, there's my A. And I can actually do this with this interactive environment. It has something called a tab completion. So if I do A dot and then type tab, it actually shows me what options are available. And these are all the different kind of matrix related things. And inverse should be one of those. Yeah, inverse. So that's kind of almost like a built-in documentation thing. It's not, but it's kind of like a documentation. Okay, let me put in V, Shift, Insert again. Okay, I don't know why that took so long. Okay, so I can do A dot inverse and times V, and that gets me something. Let me move this up. I don't want to move my gaze too far down. Yeah, so it has the same issue. So I was testing this out earlier, and this is one of the ways in which SageMath is not quite as user-friendly as Mathematica, which could be the reason you would use Mathematica, because it's easier. But there's a way to do it. So let me show you that much way. Yeah, simplified expression. All right. So now if I do this, simplify A dot inverse dot V or times V, it actually won't simplify anything. I'm pretty sure that's because this function is not written as a vector, whatever. So you need to figure out a way to do this. And this is how I found a way to do it. So let me put this result into a vector. So solution is equal to A inverse times V. And so this actually gives me access to each of those elements addressable by their index. This square bracket with an integer, that's the Python way of addressing arrays. That's why when I go out of range, it complains. And each of these have their own like a function-related methods. I don't know if I can. Yeah, I can't quite access it this way. So let me put it into its own variable. Then it'll show you f dot, and the tab completion will show all these different things. And one of them is a simplify. Simplify. And if I do that didn't do anything, but there was more. There's a simplify full. Okay, now that looks more promising. Let me compare that, f simplify full, with that, R2V1, R3V2. Yeah, that's the same result. That's what we got before. So, and so I only put it in F so that I can access this tab completion. You can actually do it directly out of here. Simplify full. So there's that. That's I1. This is I2, and this is I3. And this is how you can use a computer algebra system to solve system of equations in a programmatic way. And I guess I'm out of time to do a more realistic example, as in, something that involves more than system of 3 equations. Because when it has like 4, 5, 6 equations, that's where you can actually see, oh, yeah, it's worth learning computer algebra system because this is way too complicated. But I guess I'll end it here with this demonstration. And this is one of those things that you don't really have to know for this class. I won't be asking you any questions where you are required to use computer algebra system, but it's something that you will likely be using, and some version of it, not necessarily Mathematica, not necessarily SageMath, maybe MATLAB. MATLAB is more popular in the engineering world, or maybe some other proprietary version. But that's the tool of the trade, because engineering and scientific research at some point involves analyzing a complex and complicated system, and at some point you have to let the computer do it. You are the person who programs the computer so that the computer calculates it correctly, but yeah. So yeah, let me leave that here. I think that's probably good. Stopping point. Sorry, I'm trying to remember if I forgot anything that I should cover. Any questions? Don't think I haven't seen any questions in the chat. Yeah, I think I covered everything. Yeah, I wonder. Yeah, well, let me not do more Python stuff. Although, yeah. So with the SageMath, sometimes so it uses Python-like syntax, but it's like its own language. Yeah, so not everything necessarily available in Python is probably available here. So, anyways, I think that's a good place to end. That covers everything: demonstration of computer algebra system, and so this is the setup for the question, and I guess the question itself is fairly simple, but I want you to highlight it specifically because this is a really common arrangement that you will see when you work with the circuit. So colloquially, or maybe even officially, it's called the voltage divider. And it's a kind of a thematic theme that you will see, not just dealing with resistors, but dealing with resistors and capacitors, or resistors and inductors. When you're building passive filters, the starting place for design of things like low pass filter, high pass filter is the voltage divider. So I want you to talk a little bit about this and work out this question. So as the question says, this rather simple circuit is known as a voltage divider. The symbol consisting of three. So that's the reference for ground. Widely, that's what I'm saying. Okay. So let's work out the question A, and I'll briefly say why it's called voltage divider. So it asks, what is the output voltage of the circuit here in terms of these? Okay, so I think the way to do it is whenever you're solving a circuit, it's really useful to have information about the amount of current through different branches of circuit. Here, it's actually a pretty simple circuit, voltage in series with the two resistors. So the working out the current there actually will be simple. The equivalent resistance of these two series resistors will be R1 plus R2. So with that equivalent resistance, using Ohm's law, the amount of current through this circuit with one equivalent resistor will be amount of voltage you apply divided by the equivalent resistance is equal to V in divided by R1 plus R2. So that's the amount of current, and knowing the current, I say is useful because once you know this one dynamical quantity, then any other dynamical quantity that you are asked about, you can solve for that in a single step. So for example, they are asking us about V out, and that looks like that's the voltage change from 0 volt here to this point here, delta V. If I know the current through R2, then I can use Ohm's law again. The current times this resistance will give me the voltage change across R2. And it should be a drop from here to here. So looking at the circuit, no current is going out here. So all of the current going out here. This is the I that we calculated. That is the current through R2. So we can work out, oh, so the delta V here is the current V in divided by R1 plus R2, 2 times the amount of resistance, R2. And let me simplify this expression a little bit. Simplifying it, the V out is equal to the kind of the ratio of the resistances, R2 divided by R1 plus R2 times V in. And this appearance of expressions is, that's why it's called the voltage divider, because it divides the input voltage according to the fraction that you can calculate using the resistance values. So the value of the resistance that the voltage measurement is across divided by the total resistance that the series element thing is. So like if you had I don't know, a 9-volt input, and let's say you want to get a 5-volt out, then a really easy way to build a circuit that does exactly that would be to pick resistance values of R1 equals, I don't know, 400 ohm and R2 of 500 ohm, build that, and you will have 5-volt output. Now, if you are actually doing that, then there are some things to worry about. So when the circuit, the voltage divider circuit is actually in usage, you won't have a V out that doesn't connect to anything. So that's what this load resistance setup is illustrating. It's showing you the setup where this output voltage is connected to something that draws some power, does some stuff. So there's a load resistance. Let's redo this calculation and see how the expression for V out changes. So we can do more or less the same analysis we had before. I guess what I need to do is I need to insert an additional step here to calculate what I'm going to call R2 prime. It's actually an equivalent resistance for these two resistors in parallel. So that calculation would go like 1 over R2 prime is equal to 1 over R2 plus 1 over RL, or solving for R2 prime, it'll be, I'm just doing that mental math in my head, RL divided by RL plus R2 times R2. I think that's right. In the limit where RL goes to infinity, this will be this value. Yeah, this ratio goes to 1. And in the limit where RL goes to 0, this thing goes to 0. So with this value of R2 prime, we can actually just reuse the rest of the stuff. Because if I'm imagining replace this with a single resistor, then everything is back to what this was. So I could say, so here the answer was R2 divided by R1 plus R2. And here I can basically, wherever I see R2, I can replace that with the R2 prime. So it'll be R L over RL plus R2 times R2, that's R2 prime, divided by R1 plus the same thing, RL over RL plus R2 times R2. And I guess there's a simpler way to write it, but I think that's good enough for the answer to put into my open math. And I will show you the thing to caution about. So this is gonna be, let me just use this here, variables. R2 divided by R1 plus R underscore 2 times, I always forget this. There's times V in here, and also there's times V in here. Because it's asking for voltage, it's not asking for the ratio of the voltages. So V in, that's the right variable. Okay, so that's A. And for B, again, you can simplify it, but let me just use this. I can just do copy, paste, and just do modification of the expression here. And the way MyOpenMath evaluates these, it does it by plugging in some random numbers. So, the fact it doesn't check for if it's simplified or not. There are things I can do to the check. I don't, because I don't really care that much about simplification. And in this context, I don't think simplifying it gives you any insight. So I'm fine just leaving it in that form. So yeah, those are the answers. And this is the thing I want you to caution you about. So let's take the example that I used. Imagine I had a 9-volt power supply that I wanted to get down to 5 volts for some usage. So my input voltage is 9 volt, and I chose these two resistor values based on what's in my drawer, and let's say they seemed reasonable at the time when I picked them. So let's say I have this hooked up to some load that's drawing that it's a fairly large amount of it has a fairly large resistance. Let's say my load was 10 kilo ohm. Then so my V out will be, let me see. Let me just write it out. My V out would be R2 divided by R1 plus R2 times V in. So in the case of the ideal case, I get 5 volts as I want it. But when I replace this with the new value of a voltage that's actually going to come out of it here, then this is what ends up. So I replace the R2 on the numerator with R2 prime, and let me replace the R2 in the denominator with what's going to be R2 prime. So when I do that and put this through decimal approximation, with this 10 kilo ohm load, instead of getting 5 volts, I get 4.9 volts. Maybe that's perfectly fine. You build in 10% tolerance, you can handle as low as 4.5 volts, and you're fine. And if that's the regime where your circuit worked, that's great. But imagine a different scenario where your load resistance is, I don't know, maybe as low as 50 ohm. There are some devices that's built around the 50 ohm terminal resistance? Well, 50 ohm resistance. Then that same expression, now it's getting 0.92 volts. So you might think then, okay, so I guess I want these resistances to be really low. So let me say R1 is 4 and R2 is 5, so that when I trying to use it with the RL of 50 ohm, it'll work fine. Okay, that's one way to tackle the problem. And what I would leave it for you is to try working out the power dissipation for this circuit with this R1 of 4 ohm and R2 of 5 ohm and applied voltage of 9 volts. How much power this dissipates passively with no load connected? So that's the kind of the things that you have to worry about. You have to design around when you are working with the real practical circuits. So in real practical circuits, when you need to go to lower voltage, you only use a voltage divider for that specific purpose when you are in low power situation with active circuits, semiconductors, operational amplifiers, transistors. There are more efficient ways of doing it. Just using voltage divider, it's a great way to get a particular value of voltage that you are aiming to get, and there's application of that all over the place. It's not a very practical way or efficient way to do a voltage regulator that will reduce a particular input voltage to a lower voltage as a kind of power source. So anyways, I want you to cover that. So I've done it now. I don't need to do it again. Now, let me try to go through this question as quickly as I can because so yeah, it says it's a surprisingly difficult circuit, and here's why. When you look at all these resistors, none of them are in series or parallel with each other because the way this network is constructed, um, like they all have these junctions, so none of them are in series, and none of them are in parallel because no two resistors have same current. Like if these resistances were swapped, then it might be easier because then you can use symmetry, no current is flowing through here, and so on. But because of this asymmetry, it's gonna be a difficult circuit. So really the only way to approach this is to use Kirchhoff's rules. Kirchhoff's rules, as it says. So Kirchhoff's rules. So the first set of rules I want to use is the junction rule, which says that you add up all the currents coming in into a junction, you add up all the currents going out of a junction, and they should add up. So it looks like the question labels current through each resistor that way. So let me use the same label. So I'm gonna say there's current I1, I2, I3, I4, and here let me deliberately give the wrong direction of current. So I'm gonna say, so I think, because I think the current is supposed to flow this way, but let me say, oh, I didn't know that. I'm gonna say, this is my current I5. And you will see in the solution something that tells you that you just need to flip the direction of current. All right, so I have all those current labeled. Let's count the junctions. That'll tell us how many times we can use the junction rule. I have 1, 2, 3, 4 junctions. Yeah, that's why it's surprisingly difficult. So I can use up to 3 of those junctions. I need to leave, so there are 4, I need to leave 1 unused. So let me just not use this one and write down junction rule equations for 1, 2, and 3. Oh, I think I need one more label, this. So this is going to be my current I through the main branch of the circuit. So, okay, let me quickly write down these junction rule equations. First equation, coming from this junction, current I is what's coming in. That should be equal to I1 plus I2, two currents going out. Junction 2, so I1 is coming in. That should be equal to I3 and I5 that's going out of that junction. Junction 3, I have currents I3 and I4 coming in. Sum of those two should equal the current going out, I. Yeah, 3 equations. Okay, the next set of, so it looks like I have 1, 2, 3, 4, 5, 6 unknowns. So I'm going to need 6 equations. Using junction rule 3 times gave me 3 equations. So I know as I go into considering the loop rule, I know I have to use it 3 times so that I have a total of 6 equations that are hopefully independent of each other. So loop rule says if I add up all the voltage changes as I go around the loop, they add up to 0. So I have to define these loops. Let me do it this way. I'm going to do slightly less than orthodox way of doing this. Let me start from here, and I'm going to define one of the loops this way. Just choose a branch and go this way. This is going to be my loop 1. Sorry, my first loop, which I will label it as loop number 4 because it's going to give me equation number 4. And I could define all my loops around here, but let me do the weird thing and just use the same starting point. And I will just make different choices at each branch. This time I'll go down this way and come back to the same point. That's going to be my loop number 5. So what's important here is that these loops don't completely overlap with other loops. So here, for example, if I chose this loop, that would be bad because this loop would completely overlap with these other 2 loops. I really need something that will cover here. So let me go back and let me give this a try. I could start from the same starting point. I'm being weird. let me go around here. And here, I don't have any different choice to make here. I could just go with my second choice. And then now here, I can make a different choice. I can go across this register this way, and then down this way, and come back to finish the loop. This is maybe a little more complicated than it needs to be, but hey, I'm not gonna do the algebra by hand. I'm gonna use SageMath, so I think it'll be doable. So let me write down my 3 loop rule equations. Oh yeah, so this is gonna be equation number 6. So equation number 4. I go across the battery. That's gonna give me epsilon of voltage rise. And as I go across register R1, I will get a voltage drop of I1 R1. As I go across register R3, I'll get voltage drop of I3 R3. And then I have to go across this internal resistance, so minus I lowercase r. All of the change equals 0. Equation number 5, I start the same across the battery. And then here I'm going over R2, so minus I2 R2 minus, and then I'm going across R4, I4 R4, and the rest of the return trip is the same. Final, 6th equation, same start, voltage rise minus, so here I went this way. So minus I2 R2. And here, watch carefully. The direction the loop is going is opposite of the direction I labeled my current. So I have to remember that there's a voltage rise going across the R5 register. So plus I5 R5. And then as I go through R3, it's minus I3 R3. And I still have to return through the internal resistance, minus IR is equal to 0. So that's all my questions. Let me, by the way, change this letter E, because thinking of using SageMath, capitally, it's got its own special meaning, and I think conflicting with that is going to be a pain. So let me just change this all to be V. That's my preferred symbol over EMF anyway. So I'm just going to use V. Okay, so that's really all the physics steps, and what I need to do here is just to write out this set of equations. Sorry, I gotta point this out better. Let me move these equations so that I can kind of see them as I work with the SageMath. So again, if you want to figure out how to, if you want some help using the equation solver, then to help solve, that'll give you the syntax for the function and give you some examples. That's what I find the most useful. So I'm gonna define all the variables. I have I1, I2, I3, I4, I5. I think that's it. And I need the resistances, lowercase r, R1, R2, R3, R4, R5. And then I need the voltage V. I think that's all. Okay, I need to write out my equations. Let me do it this way. I'm gonna build on, can I do that on the right? Let me just do equation 1. That's I is equal to I1 plus I2. Equation 2, that's I1 is equal to I3 plus I5. Equation 3, that's equal to I3 plus I4 is equal to I. Equation 4, V minus I1 times R1 minus I3 times R3 minus I times lowercase r is equal to 0. Equation 5, V minus I2 times R2 minus I4 times R4 minus I times R is equal to 0. Equation 6, V minus I2 times R2 plus I5 times R5 minus I3 times R3 minus I times R is equal to 0. Okay, let's put all these into an array and make sure they look the way they are supposed to look. So equations. Yeah, just compare, make sure there was no typo.
Good. Some orders might change. Just watch out for that. So I say, okay, I want the solution. This time I'm just gonna put it into solutions array. So I'm gonna solve the equations I have in terms of my unknowns. I believe they are, yeah, all the currents. So I'll say, give me all the currents. I1, I2, I3, I4, I5, my 6 unknowns. So it's pretty quick because these are actually fairly simple equations, and for computer it's relatively easy to solve them and give you an answer like this. Now algebraically they are kind of a pain to look at. So other than to ensure, okay, so I got double nested array, so I really want to look at the first and the only element, and they have first, the second, third. Okay, so if I'm looking at the first element, that's that second element. So once you get the hang of what solutions are given, then the rest of the things to do is to just plug in the numbers. So I'm going to use the substitution sequence, the syntax that I was using before. So this gives me this expression to which I can plug in numbers for all these. So I'm going to substitute in the internal resistance of 5 ohm, resistance R1 of 15 ohm, oops, resistance R2 of 10 ohm, resistance R3 of 10 ohm, resistance R4 of 15 ohm, resistance R5 of 5 ohm. And let's hope it's, oh, I need to plug in voltage as well. So voltage of 20 volts, 3 of 20. Yeah, that's it. That's the total current I1, or the I. And let me just get the all the other answers so that I can just plug them all in. So that's I1, that's I2, and I1 plus I2 should give I. That's I3, that's I4, and finally I5. There is some symmetry here, you know, these, but like not all that useful. So I5, this current, when I get a numerical answer, you see that it's a negative. And that's what tells you the direction of current that I picked here, it's the wrong direction. And so or it's not the physical direction. So I need to flip it for the actual direction the current goes. So I think for the purpose of entering the answer, they want all the positive answers. So I won't include this minus sign when I enter the answer. So entering the answer. Let's see here. So I of 1.167, IR1 of 0.5, IR2 of 0.66, 0.667, IR3 of 0.667. Maybe you could have guessed that these two currents will be the same. I don't know. I4 of 0.5 and IR5 of, I'm just going to put it as a positive number, 0.167. So yeah, that's it. Now, where does how much power is dissipated in the internal resistance of the battery? Oh, I see. So here I just use the formula or the expression. So whenever you're dealing with resistors, what I would recommend as the power formula is this one. Power dissipated in a resistor is current squared times R. This form, so you know, there were other expressions for power. Power is, you know, current times V, or V squared over R. Using these expressions correctly, dealing with the register sometimes takes care. And when you use this expression, that kind of eliminates opportunities for mistakes. So that's why I recommend this. So I can just do that. I already know the current through the resistance R. So I can just say I squared R. Oh, and this is how you can use the SageMath. So if I simply write out I squared times R, it just gives me symbolic expression that doesn't tell me anything, right? And so you could take this and
and copy and paste this, but you actually don't have to do that. Let me do it this way. So I'm gonna take the solution here, which I know gives me that equation, and I'm going to put that into the substitution sequence. So this is my algebraic expression. I'm going to substitute in that the value that that equation I equals that implies. I just need R, so let me just do a second substitution. That seems easier. R is equal to 5. So yeah, 6.81 watt. I guess that feels large, but I think it's fine. 6.81. Yeah, it's kind of large, but you have fairly large voltage and small resistance, so I think that's right. So yeah, this is the one of the circuit examples, and so this is it's a circuit that involves a system of 6 equations, and I will tell you that that's not even the hardest circuit you might see, which is why I'm introducing use of SageMath, because once your number of equations goes above 3, doing it by hand can be super tedious. And that's where it's like multiplying 2 4-digit numbers together. Like if I had to do it, I can do it by hand, but I wouldn't choose to do it. I'll just use a calculator. If I have to solve a system of 6 equations, I can do it. I know how to do it. But if I had a choice, I would just whip out SageMath and just have it do the solution with a simple function called the solve. Like that's what I would do. I would simple function called the solve. I have to do that in one line. My job is to figure out what the equations are and type it into the computer algebra system. And computer algebra system will do the tedious algebra.